The cosmos holds a secret we are desperate to learn. Are we truly alone in this vast universe? For centuries, this was a question for philosophers and dreamers, but right now science is delivering answers. We are going to explore 30 groundbreaking cosmic discoveries that have completely reshaped our understanding of where life could exist. These are not just theories. They are real findings from the surfaces of alien worlds and the atmospheres of distant planets, the strongest hints yet that we are not the only ones. You will see the evidence that has scientists whispering about oceans hidden beneath ice, strange gases that should not exist, and signals from the void that defy explanation. What does it mean that a poisonous cloud on Venus mimics a sign of life? How could a distant world's atmosphere contain a molecule only made by living organisms here on Earth? The universe is speaking, and we are finally learning how to listen. What would change for you if we discovered we were not alone? The first major clue came not from a distant star, but from our closest planetary neighbor. In 2020, astronomers announced a finding so bizarre it seemed to defy all logic. They had detected the spectral signature of phosphine gas in the upper atmosphere of Venus. On Earth, phosphine is a molecule that is notoriously difficult to create. It can be made in laboratories, but in nature, it is almost exclusively a byproduct of anaerobic life, microbes that thrive in environments without oxygen. We find it in swamps, in the depths of lakes, and in the intestines of animals. It is a gas that, for all intents and purposes, should not exist in the free air of a rocky world without a biological source. And yet, there it was, wafting through the acidic clouds of a planet we thought we understood. This discovery ignited a firestorm of debate that continues to this day. One side of the scientific community argued for extraordinary, unknown chemistry. They scrambled to find a way that Venus's hellish environment could produce phosphine without any life involved, perhaps through volcanic activity or reactions with its unique surface minerals. So far, no proposed non-biological process has fully explained the amount of gas that was observed. The other side holds firm, suggesting this could be our first real whiff of alien biology. They point to a remarkable fact about Venus. While its surface is a crushing, scorching inferno hot enough to melt lead, its cloud decks about 30 miles up are surprisingly temperate. The pressure and temperature there are almost comparable to conditions on Earth. It is within this strange, aerial habitat that scientists speculate a form of microbial life could potentially float, protected from the extremes below. This single discovery forced us to completely redefine the habitable zone, proving that life, if it exists, might be far more ingenious and resilient than we ever dreamed. While Venus teased us with a ghost in its clouds, our other neighbor presented a puzzle buried in its very soil. The red planet Mars, long a canvas for our hopes of finding life, has been giving up its secrets one grain of sand at a time. Rovers like Curiosity and Perseverance have been trundling across the ancient landscape, acting as robotic geologists. They drill into rocks, scoop up soil, and analyze the samples in their onboard laboratories. What they have found is profound, a treasure trove of complex organic molecules. Now, organic molecules are not life itself. They are the fundamental building blocks, the carbon-based Legos from which all life on Earth is constructed. They can be formed through non-biological processes, the simple chemistry of a planet doing its thing over billions of years. But finding them on Mars is a game changer. It proves that the raw ingredients for life were not only present but were being mixed and stored on the Martian surface. The real intrigue, however, lies not just in their presence but in their patterns. Scientists are not just finding simple chains of carbon, they are discovering more complex structures like thiophenes. On our own planet, thiophenes are found in coal, crude oil, and even in white truffles, often as a byproduct of biological processes. So when we see them on Mars, it forces a critical question. Are we looking at the faded chemical signature of ancient Martian microbes, or just the result of a fascinating but sterile geological history? The answer may be within our grasp. The Perseverance rover is not just analyzing these materials, it is carefully sealing the most promising samples into ultra-clean tubes and depositing them on the surface for a future mission to collect. This is the first step in an audacious plan, a robotic relay race that will culminate in those pristine Martian rocks being launched back to Earth. In our most advanced laboratories, free from the limitations of a rover's tiny onboard lab, we could search for the ultimate evidence, not just the building blocks of life, but its fossilized forms or its distinctive chemical patterns. We are collecting the evidence for a trial, and the verdict on whether life ever called Mars home is now closer than ever before. As we search for life's ingredients on our neighboring worlds, a tiny, icy moon orbiting Saturn delivers a message from a hidden ocean. The Cassini spacecraft performed a breathtaking maneuver, diving directly through enormous geysers erupting from the frozen surface of Enceladus. It was not merely sampling water vapor, it was tasting the contents of a vast subsurface sea. The analysis revealed something extraordinary, a specific mix of chemistry that sent shockwaves through the scientific community. Cassini detected tiny particles of silica, fine-grained sand, and an abundance of molecular hydrogen. This particular combination is a cosmic fingerprint. On Earth, we see this exact recipe only in one very specific environment: hydrothermal vents on the deep ocean floor. These are not just cracks in the crust, they are natural reactors. Superheated water, rich in minerals, spews from these vents, reacting with the surrounding rock to create silica nanoparticles and molecular hydrogen. The hydrogen is the crucial piece. It serves as a potent food source for microbes. Around these vents on our planet, in total darkness, entire ecosystems thrive, independent of the sun's energy. The discovery on Enceladus strongly suggests that this same powerful process is happening right now, deep beneath its icy shell. This means Enceladus possesses all three fundamental requirements for life as we know it. It has liquid water in its global ocean. It has the essential chemical elements like carbon, nitrogen, and oxygen. And now we know it has a lasting, accessible energy source. A world once seen as a frozen ball of ice is now one of the most promising places in our entire solar system to look for living organisms, a testament to the fact that the most vibrant habitats may be hiding in the darkest, most unexpected places. The mystery of Mars only deepens with the air itself. Another rover, Curiosity, has been sniffing the Martian atmosphere for years, and it keeps finding something that should not be there: methane gas. This is not just a one-time reading, it is a puzzle that changes with the seasons. The background level of methane is low, but then, suddenly and unpredictably, it spikes to many times its normal concentration. On our own planet, this pattern would be a clear alarm bell. The vast majority of methane in Earth's atmosphere is biologically produced. It comes from wetlands, from the digestive systems of livestock, from the decay of plants in landfills. It is a gas of life, so when we see these same erratic bursts on Mars, the immediate, thrilling question is whether we are detecting the faint, cyclical breath of a hidden biosphere. Of course, scientists are a cautious bunch, and they have explored every non-living explanation. There is a geological process called serpentinization, where certain rocks react with water deep underground, and this can slowly produce methane. The problem is that this kind of process should release the gas at a relatively steady, slow trickle. It does not easily explain the sudden, dramatic plumes that instruments have detected. These spikes behave more like a burp than a steady leak, as if a reservoir of the gas is being released all at once from a specific, localized source. If that source is not a curious rock formation, then what is it? The search is now a planetary-scale detective story. The ExoMars Trace Gas Orbiter, a spacecraft specifically designed to analyze the Martian atmosphere, is scanning from above, trying to correlate these methane spikes with specific locations on the surface. The goal is to triangulate the signal to find the very spot where this potential biosignature is emerging from the ground. Is it coming from an ancient subsurface aquifer where microbial life might still cling to existence? Is it seeping from a long-sealed cave system that has protected a remnant ecosystem for eons? Each strange whiff of gas is a clue pointing us toward what could be the greatest discovery in human history. But the hunt for life's ingredients does not end with watery oceans. Far beyond Enceladus, another of Saturn's moons, presents a vision of an almost familiar yet utterly alien world. Titan is a place of staggering complexity, wrapped in a thick, hazy atmosphere. When the Huygens probe descended through those orange clouds and landed on its surface, it revealed a landscape that sent chills down the spines of every scientist watching. Titan has rolling hills, vast sand dunes, and most incredibly, a full liquid cycle complete with rain, rivers, and lakes. But this is not a water cycle. The rivers that carve through the terrain and fill the Great Lakes are flowing with liquid methane and ethane, substances that are gases here on Earth but exist as liquids in Titan's deep freeze. It is a world that mirrors our own in form, yet is built from entirely different materials. The Cassini spacecraft orbiting above analyzed the moon's thick atmosphere and found it to be a colossal chemical factory. Cosmic radiation and sunlight bombard the methane and nitrogen in the air, triggering a cascade of reactions that build increasingly complex organic molecules. These molecules clump together, raining down continuously onto the surface in a slow, steady drizzle of organic material. One of the most tantalizing discoveries was vinyl cyanide. To us, that name might sound like a toxic chemical, but on Titan, it could be the key to a completely different kind of life. In Titan's frigid methane seas, this molecule has a unique property. Scientists theorize it could spontaneously assemble into hollow, microscopic spheres, structures they call azotosomes. These would be stable, flexible bubbles acting almost like cell membranes. On Earth, our cell membranes are made from lipids and need water to form. On Titan, vinyl cyanide could perform the same essential function, but in liquid methane. This means Titan is not just demonstrating that the building blocks of life can form elsewhere. It is showing us that the very architecture of a cell, the container that holds life together, might be possible in environments we once considered utterly hostile. We are looking at a natural laboratory the size of a planet, one that is actively conducting experiments in a chemistry we are only beginning to understand. The chemistry of distant moons is being written in water and ice. While Titan presents a strange mirror of our own world, another moon promises a more familiar kind of ocean. Jupiter's Europa gleams like a cracked marble in the void, its surface a global shell of ice. For decades, scientists have been certain that a vast, salty ocean churns beneath that frozen crust, an ocean containing more than twice the volume of all the water on Earth. The great mystery was whether we could ever hope to reach it, buried under ice that could be miles thick. Then, the Hubble Space Telescope saw something that changed everything. On multiple occasions, it observed what appeared to be gigantic plumes of water vapor, erupting hundreds of miles into space from fractures in Europa's icy surface. These are not confirmed beyond all doubt. The detections are tentative and require follow-up, but the evidence is incredibly compelling. They suggest that Europa, just like Enceladus, is actively venting the contents of its hidden sea directly into space. Think about what that means for our search for life. A future spacecraft would not need to land, drill through kilometers of ice, and send a submersible into the dark depths, a monumental engineering challenge. Instead, it could simply fly through one of these plumes, just as Cassini did at Enceladus, and taste the ocean itself. It could analyze the salt content, search for complex organic molecules, and even look for the chemical signatures of biological processes. These plumes are more than just geysers. They are a direct pipeline from an alien ocean to the vacuum of space, offering us a free sample of a world we once thought was locked away forever. Their very existence tells us that Europa is not a dead, frozen ball. It is a geologically active world with energy coursing through its core, likely driven by the immense gravitational tug of war between Jupiter and its other large moon. This constant flexing heats the interior, keeping the ocean liquid and potentially driving the very chemistry that could support life. We are no longer staring at an impenetrable ice shell. We are looking at a world that may be actively broadcasting its secrets if we are only clever enough to listen. The search for a second Earth leads us 40 light-years away to a quiet, cool star known as TRAPPIST-1. This red dwarf is home to a stunning planetary family, a system of 7 rocky worlds, each one remarkably close in size to our own. 3 of these siblings orbit firmly within the star's habitable zone, that precious region where temperatures could allow for liquid water to pool on their surfaces. This discovery alone was monumental, a solar system packed with Earth-sized candidates all in one place, but the real investigation has only just begun. The James Webb Space Telescope has now turned its immense eye toward this system, not to take pretty pictures but to perform a kind of cosmic blood test. As these planets pass in front of their star, Webb analyzes the starlight filtering through their atmospheres. It is searching for the specific chemical fingerprints of gases like oxygen, methane, and carbon dioxide. The presence of these molecules, especially in certain combinations, could be the telltale sign of a living world. Imagine an atmosphere rich in oxygen and methane simultaneously. On Earth, these gases react with each other and disappear quickly. Their persistent coexistence is a clear signal that something, most likely life, is constantly replenishing them. Finding such a balance on a TRAPPIST world would be the strongest evidence for biology we have ever seen, yet this promise comes with a profound challenge. Planets orbiting so close to a red dwarf star are likely tidally locked. One side of the planet would be in permanent, scorching daylight, while the other is trapped in eternal, frozen night. The question is whether life could survive in the thin, temperate ribbon of twilight that might circle the planet between these two extremes. Could powerful winds distribute heat from the day side to the night side, creating a more hospitable environment? Or would the stark contrast create a world of violent weather, making it impossible for life to gain a foothold? This system is a perfect natural laboratory, a collection of similar worlds placed at different distances from their sun, allowing us to test the very limits of habitability. The answers are already streaming in, not as a simple yes or no, but as data points on a graph, each one bringing us closer to understanding what makes a world alive. The promise of the TRAPPIST system is profound, but an even more specific and tantalizing clue has emerged from the data stream of the James Webb Space Telescope, focusing on a single, distant world known as K2-18b. This is not just another exoplanet, it is what scientists call a Hycean world, a completely new class of planet that could redefine our entire concept of habitability. Imagine a planet significantly larger than Earth, but not a gas giant, a world completely enveloped by a deep, global ocean beneath a thick, hydrogen-rich atmosphere. K2-18b is this world, and it orbits within the habitable zone of its star. When Webb analyzed the starlight filtering through its atmosphere, the results were staggering. The telescope clearly detected the presence of carbon dioxide and methane. This alone was a monumental find, confirming that this water world possesses the fundamental chemical cycles that, on Earth, are intimately tied to life. But it was a second, far more tentative signal that sent a shockwave through the astronomy community. The data contained a faint, unconfirmed hint of another molecule, dimethyl sulfide. To understand why this is so electrifying, you have to come back to our own planet. In Earth's oceans, microscopic phytoplankton, the foundation of the marine food web, release dimethyl sulfide as a waste product. This gas floats into the atmosphere, and it has no known non-biological source on our world. Its presence is a direct gaseous signature of aquatic life. So, the potential detection of this same molecule in the atmosphere of a distant water world is arguably the most compelling hint of alien biology we have ever encountered. It suggests the breathtaking possibility that the vast, dark ocean of K218b might not be sterile, that it could be teeming with its own version of phytoplankton, a living haze slowly exhaling a signal across the light years. Scientists are quick to temper this excitement with caution. The signal is faint, and it requires follow-up observations to be confirmed. Rival explanations involving strange and unknown atmospheric chemistry must be ruled out. But the very fact that we are now having this conversation, debating the possible biological source of a gas on a world 120 light-years away, marks a turning point in human history. We are no longer just looking for planets where life could exist. We are starting to sniff the air for the specific chemicals that life leaves behind. That faint chemical whisper from a distant water world is a marvel of modern science, but decades before we could analyze alien atmospheres, we were simply listening. And on one quiet August night in 1977, the universe seemed to shout back. It was the Big Ear radio telescope in Ohio, methodically scanning the sky for any sign of intelligent signals, when it recorded a burst of radio waves so powerful and so strange that the astronomer reviewing the data, Jerry Amon, simply circled it on the printout and wrote one word in the margin: "Wow." This was not random cosmic static. The wow signal was a narrowband transmission, a sharp, pure tone concentrated on one specific frequency. In the vast, noisy symphony of space, natural objects like pulsars or quasars create a broad racket across many frequencies. This signal was more like a laser beam compared to a floodlight, precisely tuned to the quiet frequency of neutral hydrogen, a logical channel for any civilization trying to announce its presence. It lasted for 72 seconds, the exact duration the Big Ear telescope could focus on a single point in the sky, and then it vanished, never to be heard again. For decades, this single event has been the ghost in the machine of the search for extraterrestrial intelligence. Every conceivable explanation has been put on trial. Could it have been a secret military transmission, a reflection off a piece of space debris, or a passing satellite? Meticulous investigation has ruled out every human-made source. The signal did not repeat, and its specific characteristics do not match any known natural celestial phenomenon. The very thing that makes it so compelling, its perfect, artificial-seeming structure, is also what makes it so frustratingly unique. Newer analyzers have tried to pinpoint its origin with modern star maps, suggesting a possible link to a sun-like star in the constellation Sagittarius, but this remains a theory, not a confirmation. The WOW signal stands alone, a single, brilliant flash in the cosmic dark. It is a reminder that our search is like watching for lightning in a vast desert. We might only see a single flash in a lifetime, but that one flash proves beyond any doubt that a storm is possible. It tells us that the universe is capable of producing a signal that looks exactly like a message, and that sometimes the most profound mysteries are not in the data we collect, but in the silence that follows. That single, unexplained radio burst left us listening for a reply that never came, but sometimes the universe sends a messenger instead of a message. In October 2017, astronomers in Hawaii spotted something unprecedented. A strange object hurtling through our solar system on a path that could only mean one thing: it was not from here. This was Oumuamua, the first confirmed visitor from interstellar space. Its name means scout from the distant past in Hawaiian, and it lived up to that title with a series of bizarre mysteries. The first was its shape, Based on the way its brightness fluctuated as it tumbled through space, scientists determined it was highly elongated, perhaps 10 times longer than it was wide, a shape like a cosmic cigar or a pancake. Nothing in our solar system looks quite like it. The second puzzle was what it was not doing. As a small object from the cold depths of space approaches the sun, the ice on its surface is expected to heat up and vaporize, releasing gas and dust that forms a visible cloud or coma around it, the defining feature of a comet. Oumuamua had no coma. It showed no visible outgassing at all, appearing as a barren, inert rock. Then came the biggest mystery of all, its acceleration. As Oumuamua sped away from the sun, something was giving it an extra push. Its trajectory could not be explained by gravity alone. It was experiencing what scientists call non-gravitational acceleration. For a normal comet, this is easily explained. The jet-like force of outgassing acts like a weak rocket engine, nudging it off a purely gravitational path. But Oumuamua had no visible tail, no plume of gas or dust for telescopes to detect. This left astronomers scrambling. One leading natural explanation suggests it could have been a chunk of solid hydrogen ice. Hydrogen ice is virtually invisible as it vaporizes, and the outgassing could have provided the necessary push without creating a visible coma. The problem is that such a hydrogen iceberg would have evaporated quickly in the heat of the sun, raising questions about how it could have survived its long journey between the stars. This gap in our understanding led a prominent Harvard astronomer, Professor Avi Loeb, to propose a more extraordinary idea. He suggested that Oumuamua's strange shape and its mysterious, unseen propulsion could be explained if it was a piece of advanced technology, a light sail. A light sail is a hypothetical spacecraft that uses the gentle but constant pressure of sunlight for propulsion, much like a boat's sail uses wind. This would account for the non-gravitational acceleration without any need for visible outgassing. Its flattened shape would be ideal for such a function, catching the momentum of photons from stars. The scientific community remains deeply divided, with most favoring a natural, albeit exotic, origin. Yet Oumuamua's brief visit forced a fundamental question upon us when we see something truly strange in the cosmos. How long do we search for a natural explanation before we dare to entertain the possibility of artifice? It was a silent, drifting enigma that passed through our backyard and was gone before we could truly understand it. A ghost from the galactic void that continues to challenge everything we thought we knew about the visitors between the stars. The silent journey of Oumuamua reminds us how much we have yet to learn about the raw materials drifting between the stars. Yet one of those materials, the most crucial for life as we know it, is turning out to be astonishingly common. Water is not a rare treasure in the cosmos, it is a cosmic constant. Powerful observatories have peered into the swirling disks of gas and dust around young stars, the very cradles where planets are born, and they have found a definitive signature, the spectral fingerprint of water vapor. This is a profound realization. The building blocks of worlds are infused with water from their very inception, meaning that any rocky planet forming in such a system likely receives a generous delivery of this life-giving substance right from the start. This water is not just locked away in future oceans, it is also abundant in our own celestial backyard. We have detected water ice on asteroids clinging to the surfaces of these primordial rocks left over from the solar system's formation. Even the majestic gas giants like Jupiter and Saturn have water vapor swirling in their upper atmospheres, but the most stunning reservoirs of water are hidden from view, buried beneath the surfaces of frozen moons. Jupiter's moon Ganymede, the largest moon in our solar system, is now known to contain more water than all of Earth's oceans combined, a vast salty sea locked under a thick crust of ice. Its sibling, Callisto, likely harbors a similar subsurface ocean, a world that was once written off as a dead, cratered relic now holding a secret sea. This universal abundance fundamentally changes the equation for life. Water is the ultimate solvent, the universal mixer that allows complex chemistry to happen. It dissolves minerals, transports nutrients, and facilitates the intricate molecular dances that lead to biology. Finding it everywhere we look, from stellar nurseries to the depths of icy moons, means the most fundamental ingredient for life is practically a default setting across the galaxy. The universe is not just a dry, empty desert. It is a network of oases, some on the surface, and many more waiting in the dark beneath the ice. But the ingredients for life are not scattered evenly across the galaxy. We are finding that the universe has its own version of prime real estate, a concept known as the galactic habitable zone. This is not about a single star's warmth, but about the safety and richness of an entire neighborhood within a sprawling city of stars. Our Milky Way is a dynamic and sometimes violent place, and your cosmic address matters tremendously. Venture too close to the galactic center, and you find a maelstrom of activity. This crowded core is packed with stars, leading to frequent cataclysmic supernova explosions. These stellar deaths bathe nearby space in intense radiation, sterilizing planets and stripping away their atmospheres. It is a chaotic, high-energy environment where complex molecules would be torn apart almost as soon as they form. On the other hand, the quiet, sparse suburbs in the galaxy's outer reaches present a different problem. These regions formed from primordial gas that was never enriched by the remains of early, massive stars. They are impoverished, lacking the heavier elements like iron, carbon, and oxygen that are absolutely essential for building rocky planets and the chemistry of life. Our solar system, it turns out, resides in a perfect cosmic sweet spot. We orbit far enough from the dangerous core to avoid constant sterilization, yet close enough to have been seeded with a rich abundance of those vital heavy elements from generations of stars that lived and died before our sun was even born. The stunning discovery is that this privileged position is not unique. New surveys of the Milky Way reveal that billions of other stars share this same favorable orbital band, this galactic green belt. This massively expands the number of potential cradles for life, suggesting that the quiet, stable conditions that allowed our world to flourish are not a rare fluke, but a common feature of spiral galaxies like our own. The resilience of life has been tested not just on distant worlds, but in the cold, airless void itself. In a series of extraordinary experiments, scientists have placed colonies of tardigrades, also known as water bears, directly into the harsh environment of open space. These microscopic creatures, no larger than a grain of salt, were exposed to the complete vacuum, searing ultraviolet radiation from the sun and the bitter cold of the cosmos. The results defied all expectations. Many of them not only survived this brutal onslaught, but they returned to Earth rehydrated and went about their lives as if nothing had happened, even reproducing and creating healthy offspring. These tiny animals possess almost superhuman abilities. They can enter a state of suspended animation called cryptobiosis, a deep hibernation where their metabolism slows to an undetectable trickle, allowing them to withstand conditions that would instantly kill almost any other known organism. This incredible hardiness forces us to reconsider the very journey of life. It lends powerful credibility to an ancient idea called panspermia, the theory that life's seeds can travel between planets, hitchhiking on asteroids and comets. Think about the violent impacts that scar every rocky world in our solar system. A large asteroid striking Mars would blast tons of the planet's crust into space. If that ejected rock contained dormant, tardigrade-like microbes shielded deep within, they could potentially survive the journey through space. After millions of years adrift, such a rocky life raft could crash into a welcoming world like Earth, or even a moon like Europa, delivering its dormant passengers to a new home. The water bears have shown us that the building blocks of life are not just chemicals, but living creatures themselves, equipped with a stunning capacity to endure the ultimate journey. Life may not be a delicate flame that flickers out easily, but a tenacious spark capable of leaping from one world to the next across the galactic expanse. These tiny water bears show us that life can be incredibly tough, but how many opportunities does it actually have out there? For decades, that question was framed by a single, elegant formula, the Drake equation. Conceived by astronomer Frank Drake in 1961, it was less a calculator and more a structured way to articulate our ignorance. The equation multiplies a series of factors, starting with the rate of star formation and ending with the lifespan of a technological civilization, to estimate the number of intelligent species we might hope to contact. For most of its history, nearly every variable was a giant question mark. We were guessing. But today, a revolution in astronomy is transforming that guesswork into grounded science. We now have solid answers for the first few terms. Thanks to missions like Kepler, we know with certainty that most stars host planets. The fraction of stars with planetary systems, a variable called FP, is not just high, it is nearly 1. Stars with worlds are the rule, not the exception. Furthermore, we have learned that a significant fraction of those planets, the variable Ne, orbit within their star's habitable zone. They are not too hot and not too cold, at least in principle, for liquid water to exist. We now know our galaxy is teeming with billions of such worlds. This changes the entire meaning of the equation. When you plug in these new, much larger numbers, the result becomes staggering. Even if you assume the remaining probabilities are vanishingly small, the sheer, colossal number of planetary starting points means the potential for life becomes a near statistical certainty. If the chance of life emerging on any single habitable world is just 1 in a million, that still leaves thousands, even tens of thousands of living worlds scattered throughout the Milky Way alone. The equation is no longer a philosophical exercise, it is a powerful statement of probability. The universe has provided the raw materials on an almost unimaginable scale. The great unknowns that remain are no longer about opportunity but about process. How often does that initial spark of life actually catch? And once it does, how often does it evolve toward complexity and intelligence? The silence we hear from the cosmos may not be a sign of emptiness, but simply a measure of how difficult those final steps truly are. This hunt for life now focuses on the very air these distant worlds breathe. The James Webb Space Telescope is not just a camera, it is a celestial chemist performing a kind of alchemy from a million light-years away. Its primary tool for this is spectroscopy, a technique that sounds complex but is based on a beautifully simple principle. Every element and molecule in the universe has a unique fingerprint, a specific way it interacts with light. When starlight filters through the thin veil of an exoplanet's atmosphere, the gases present there absorb specific colors or wavelengths of that light. By analyzing the resulting spectrum, the precise pattern of missing colors, Webb can identify the chemical composition of an alien sky. It is like holding a prism to a rainbow and reading a story written in its dark, narrow lines. The story scientists are most desperate to read is one written by life itself. They are not looking for a single gas, but for a specific, unstable partnership, the simultaneous presence of oxygen and methane. On a sterile, lifeless world, these two gases are sworn enemies. They react with each other almost immediately, vanishing from the atmosphere. For both to be present in significant quantities, something on the planet must be constantly, vigorously producing them. On Earth, that something is life. Our plants and cyanobacteria pump out oxygen, while our microbes, wetlands, and livestock release methane. Their coexistence is a persistent planetary-scale contradiction that can only be explained by biology. Finding this same defiant pair on a distant world would be the most powerful evidence for life we could hope to detect from such a distance. It would suggest a world teeming with processes that constantly refresh its atmosphere against the tide of natural chemistry. Yet the path to this discovery is fraught with traps. A planet's geology can create false positives, tricking us into seeing life where there is none. For example, a world with vast quantities of liquid water can have its water molecules split by stellar radiation, releasing oxygen into the air without a single living cell involved. Similarly, methane can seep from volcanic vents or be produced by the reaction of hot water with certain types of rock. A detection of either gas alone is exciting but not conclusive. The key is context. Scientists are now building more robust profiles, looking for other supporting gases like nitrous oxide, which is also heavily linked to biological activity on Earth. They are modeling the planet's star, its geology, and its climate to see if a non-biological scenario can realistically explain the entire atmospheric cocktail. They are watching for seasonal variations, a telltale pulse in the gases that might mirror the growth and decay of life across a globe. This is the new frontier, a painstaking process of cosmic forensics where we must rule out every other possibility before we can whisper the most thrilling word in science: life. The journey of life may not have even started here on Earth. New evidence is transforming a once fringe idea, the panspermia hypothesis, into a serious scientific possibility. We now have physical proof that the building blocks of life are not just scattered on planets, but are hitching rides on asteroids throughout the solar system. Recent sample return missions have achieved the impossible, reaching distant space rocks and bringing pieces of them home. The Japanese Hayabusa 2 spacecraft traveled to the asteroid Ryugu, and NASA OSIRIS-REx mission visited Bennu. When scientists in sterile laboratories carefully opened these pristine containers, they found exactly what they were hoping for. The dust and pebbles from these asteroids were rich in a suite of organic molecules, including amino acids, the very compounds that string together to form proteins, the workhorses of all known biology. These are not just simple chemicals, they are the complex precursors to life, and they were delivered to Earth's doorstep on ancient, wandering rocks. This discovery confirms that the early solar system was a delivery service for life's ingredients, raining these essential compounds down on every young world. But the case for panspermia grows even stronger. Could life itself survive such a transfer? Experiments here on Earth have placed hardy bacteria like Deinococcus radiodurans in conditions that simulate the immense shock of an asteroid impact. These microbes, nicknamed Conan the bacterium for their incredible toughness, have shown they can withstand the staggering pressures of being blasted off a planet's surface. Once in space, they face a new set of threats, from intense radiation to the utter vacuum and freezing temperatures. Yet, studies on the International Space Station have demonstrated that certain microbes, when shielded within small clumps of rock, can enter a dormant state and survive for years, perhaps even decades, glued to the outside of the station. If they can endure there, could a colony survive a longer journey, nestled deep within the protective interior of a meteoroid? The emerging picture is one of incredible resilience. The universe may not be seeding life, but it is certainly seeding its potential on an interstellar scale. The amino acids raining down on a young Earth could have been the same ones falling on a young Mars or Europa, providing a universal starter kit. This means the spark that ignited life here might not have been a 1 in a trillion lightning strike, but a common cosmic event repeated on countless worlds. Life may not be a miracle unique to our planet, but a natural and perhaps inevitable process that arises wherever the conditions are even briefly right. The air of a world might whisper of biology, but what if we could see the glare of a civilization? This is the new frontier of the search, a shift from looking for the chemistry of life to hunting for the artifacts of intelligence. These potential markers are called technosignatures, and they expand our imagination from microbes to engineers. Instead of searching for methane or oxygen, astronomers are now designing methods to spot the hallmarks of a technological society. One of the most direct ideas is to look for city lights on the dark side of a distant exoplanet. Just as our own planet gleams with artificial light at night, an advanced civilization might paint its night side with a similar, unnatural glow. By analyzing the subtle difference in brightness between a planet's day side and its night side, future telescopes could potentially detect this telltale shine, a collection of billions of lamps and screens visible across the light years. A more haunting signature might be found in the atmosphere itself. We are now capable of detecting industrial pollutants like chlorofluorocarbons or CFCs in the thin air of alien worlds. These are complex molecules that do not form naturally in any significant quantity. Finding them would be like hearing a smoke alarm in an empty forest, a clear signal that an industrial process, a technology, is actively at work. It would mean we are not just detecting life, but a society that has reached a stage similar to our own, with all the power and complication that brings. The most staggering technosignature of all, however, requires thinking on a truly cosmic scale. Imagine a civilization so advanced it has learned to harness the total energy output of its home star. Theoretically, such a culture might construct a Dyson sphere, a vast swarm of energy collecting satellites encircling the star, capturing nearly all of its light. To us, such a star would look profoundly strange. It would shine brightly in the infrared spectrum, glowing with the waste heat from an unimaginable engine, while its visible light would be almost completely dimmed. Our telescopes have already flagged a handful of stars that exhibit this bizarre behavior, stars that flicker and dim in ways that defy all natural explanation. While these are almost certainly natural phenomena, their very existence trains us to look for the ultimate signature of a civilization that has transcended its planetary cradle. The search for technosignatures forces a profound question. Are we looking for a mirror or for something entirely beyond our comprehension? We might one day find a signal not from a civilization like our own, but from one that has evolved for 1,000,000 years longer, a society whose technological traces are as alien to us as a city's skyline would be to a single-celled organism. The search is no longer just for life, but for the shadow it casts upon the stars. The cosmos occasionally screams for a fraction of a second, and we are only just learning how to hear it. These are fast radio bursts, or FRBs, flashes of radio energy so intense they can outshine entire galaxies for a single, fleeting moment. They travel for billions of years across the universe, and by the time they reach our telescopes, the entire event is over in less time than it takes to blink. For years, their origin was one of astronomy's greatest puzzles. What natural force could possibly be so powerful, so focused, and so brief? The leading answer points to magnetar, which are the intensely magnetic corpses of dead stars. A magnetar is like a cosmic tantrum, a stellar remnant with a magnetic field so strong it could strip the information from every credit card on Earth from halfway across the galaxy. When one of these objects experiences a starquake, a sudden crack in its rigid surface, it can release a cataclysmic blast of energy that we see as a fast radio burst. This explanation fits for many of the one-off bursts we detect, but then there are the repeaters. These are sources that fire off not just once, but again and again, sometimes in predictable patterns, sometimes in chaotic clusters. Even more strangely, the structure of their radio waves is not a simple blast. Some show intricate patterns with multiple sub-bursts that drift downward in frequency, like a cosmic slide whistle. This complexity suggests an engine that is far from simple, a source that is somehow organized and capable of reloading and firing over and over. While most astronomers are convinced these two have a natural, if spectacular, origin, the sheer strangeness of the repeaters has led a few to keep a more open mind. Could we be seeing the occasional leakage from unimaginably powerful technology? A civilization advanced enough to need colossal amounts of energy might build a transmitter of planetary or even stellar scale. The burst we see could be a side effect, a beam of power used to push light sails across interstellar space, momentarily pointing in our direction. Or perhaps it is a beacon, a lighthouse signal meant to last for eons. The key point is not that this is the likely answer, but that for these specific, complex, and repeating signals, we cannot yet completely rule it out. They remain outliers that challenge our understanding, reminding us that the line between a natural phenomenon and an artificial one can be razor-thin when viewed from a billion light-years away. The very structures that carry life's instructions, the twisted ladder of DNA and its molecular cousin RNA, are built upon a chemical spine made of phosphorus. Without this one element, life as we know it could not exist. It is the sturdy scaffold that holds our genetic code together, and it is a vital component of the molecule ATP, the universal energy currency that powers every cell in your body. For a long time, astronomers worried that phosphorus might be a cosmic bottleneck, an ingredient so rare that it could severely limit the number of living worlds. The element is forged in the violent hearts of massive stars, but the prevailing models suggested that most of it might get locked away in unreactive forms during a supernova explosion, like ash that cannot kindle a new flame. New observations have shattered that pessimistic view. Powerful telescopes have now analyzed the light from specific types of supernova and found the clear, abundant signature of phosphorus being blasted into space. It turns out that certain stellar explosions are far more efficient at creating and scattering this crucial element than we ever realized. We can see its spectral fingerprint in distant clouds of gas and dust, the very same clouds that are collapsing to form new solar systems. This means that from the very beginning, planets forming around other stars are being seeded with this essential ingredient. The phosphorus that forms the backbone of your own DNA was once created in a cataclysm like this, a star that died so that your story could one day be written. The universe is not just providing the water and the energy for life, it is also delivering the very blueprint, ensuring that the potential for biology is written into the fabric of young worlds from their inception. The need for phosphorus reveals a universe rich with life's raw code, but the real estate for that life is turning out to be far more common than we ever guessed. Even the smallest, most distant worlds in our own solar system are whispering secrets of hidden seas. The dwarf planet Ceres, the largest object in the asteroid belt, was long considered a barren, rocky relic. Then the Dawn spacecraft arrived and transformed our view. It discovered mysterious bright spots staining the floor of the Ocata crater, glowing with a stark, brilliant white. Analysis revealed these are massive deposits of sodium carbonate, a kind of salt. On Earth, we find such concentrated deposits where salty water has recently reached the surface and then evaporated, leaving a gleaming crust behind. The presence of these fresh, bright salts on Ceres is a powerful clue that a reservoir of liquid water, likely a deep, regional ocean, still exists beneath its crust. This is not an ancient, frozen relic, but a world that was geologically active in the very recent past and may still be today. Far beyond the asteroid belt, the New Horizons probe gave us an equally stunning revelation at the solar system's edge. As it flew past Pluto, it sent back images of a vast, heart-shaped plain of nitrogen ice called Sputnik Planitia. The surface of this plain is remarkably smooth, almost unblemished. It shows a startling lack of impact craters, the cosmic scars that record billions of years of bombardment. For a surface to be that smooth, something must be actively resurfacing it, erasing those craters as they form. The most compelling explanation is that Pluto has a subsurface ocean of liquid water, a deep global sea. The heat from the decay of radioactive elements in its rocky core, combined with the unique insulating properties of the thick ice shell above, could be keeping this ocean liquid. This internal heat would drive geological activity, causing the icy surface to churn and renew itself over time. The implications are staggering. We are no longer just talking about a handful of large moons around gas giants. We are now finding that subsurface oceans could be a standard feature of icy worlds, from the asteroid belt all the way to the Kuiper belt. This multiplies the number of potential habitats in our solar system alone from a few to potentially dozens. These dark, buried seas, completely isolated from the heat of any star, are rewriting the definition of a habitable world, proving that life's true home may not be on the surface of a planet, but in the warm, dark depths beneath its frozen skin. The flood of data from the James Webb Space Telescope is not a trickle, it is a tidal wave, and it is washing away old assumptions about distant worlds. This observatory has fundamentally changed the game, giving us the power to do more than just detect exoplanets. We can now take their vital signs. For the first time in human history, we are studying the atmospheres of small, rocky planets orbiting other stars, analyzing the air of worlds that could be cousins to our own Earth. The early results are both humbling and electrifying. Webb has already confirmed the presence of water vapor in the skies of a planet like GJ486b, a rocky world orbiting a red dwarf star. It has mapped the temperature distribution on the lava-scorched day side of planets like TRES-3b, revealing a world of searing heat and global cloud cover. These are not just data points, they are the first brushstrokes in a detailed portrait of alien climates. The precision is staggering. Webb can measure temperature variations across a planet's surface from over 1,000 light-years away, telling us where the hotspots are and where the clouds gather. This torrent of information is building a new library of planetary knowledge, a reference guide for what atmospheres can look like with and without the influence of biology. The telescope is still in its early years, and every new observation sharpens its focus. Its continued gaze is our single greatest tool in the hunt for that elusive, definitive signal. In the coming years, as it stares at the most promising candidates like the TRAPPIST-1 worlds, it will gather enough light to search for the subtle, unstable chemical partnerships that scream of life. We are no longer waiting for a miracle, we are methodically collecting the evidence, and the verdict on whether we are alone may be written in the next set of data. While we scan the skies for distant biosignatures, some of the most profound evidence for life's cosmic potential is being uncovered in the darkest, most hostile corners of our own planet. These are the extremophiles, organisms that do more than just survive in places that would instantly kill almost anything else. They thrive there. Scientists have pulled vibrant bacterial colonies from rocks deep within gold mines, living completely independent of the sun's energy, feeding on chemicals released from the surrounding stone. They have found microbes swimming in the near-boiling, acidic waters of volcanic hot springs, an environment that mirrors the corrosive clouds of Venus. Perhaps most astonishingly, they have discovered a fungus called Cryptococcus neoformans growing inside the heavily irradiated walls of the damaged Chernobyl nuclear reactor, literally consuming radiation as a source of energy. These are not rare exceptions, they represent a vast, hidden biosphere that operates on entirely different rules. The discovery of extremophiles has completely shattered our narrow, Earth-centric view of what a habitable world must look like. We once clung to the idea of a Goldilocks zone, a narrow orbital band where a planet is not too hot and not too cold for liquid water to exist. But life on Earth has shown us it does not need a gentle, sun-drenched pond. It can flourish in total darkness at the bottom of the ocean, encased in ice or in briny, toxic soils. This radical adaptability means that the true habitable zone around any star is likely far wider and more varied than we ever dreamed. A world like Jupiter's moon Europa, with its global subsurface ocean, is not a frozen wasteland, it is a potential haven. The acidic atmosphere of Venus is not a certain death sentence, it is a potential aerial habitat. The methane lakes of Titan are not just a chemical curiosity, they are a potential solvent for a form of life we are only beginning to imagine. The extremophiles of Earth are our guides, showing us that life is not a delicate flicker, but a stubborn, tenacious force that clings to any opportunity, no matter how slim. They teach us to stop asking if a world is habitable and to start asking a much more exciting question: how is it habitable? The ability of a world to breathe, to hold onto an atmosphere, is one of the most fragile balances in the cosmos. A planet orbiting too close to its star risks having its entire sky stripped away by relentless stellar winds, leaving it a barren husk. This was the assumed fate for GJ1132b, a distant world locked in a scorchingly tight orbit around its red dwarf star. Astronomers believed its original atmosphere had been boiled off into space eons ago, leaving behind nothing but naked rock. Yet when telescopes finally managed to analyze the light filtering past this world, they saw the impossible. GJ1132b was not bare at all. It was enveloped in a thick secondary atmosphere. This was a sky born from fire, a new layer of air forged in the planet's own heart. The chemical composition was a volatile mix of hydrogen, methane, and the startling presence of hydrogen cyanide. This specific cocktail points to a single, powerful source, a world riven by massive, ongoing volcanic activity. The planet's interior is apparently churning so violently that it is constantly venting gases from its mantle, replenishing the atmosphere as quickly as the star can tear it away. It is a planetary engine fighting a continuous battle against its sun. This changes everything we thought we knew about survival in hostile orbits. A world does not need a gentle, stable start to potentially host life. It needs geological vitality, a heat within that can power volcanoes and recede its own sky. The presence of methane in this volcanic mix is particularly intriguing, as it is a gas that, in the right context, can be linked to biological processes. Could the volcanic vents on such a world be providing both the atmosphere and the chemical energy needed for life to take hold in the darkness? This discovery proves that a planet can have a second act, that a sky can be reborn from the very rock below. It suggests that even in the most punishing environments, the door to habitability might not be permanently closed, but held open by the planet's own inner fire. Our search for life is built on a single, profound assumption that it will look something like us. Every probe we send, every telescope we point, is calibrated to find the chemistry of life as we know it. But what if we are searching with blinders on? This brings us to a revolutionary concept known as the shadow biosphere. Imagine a form of life existing right beside us or on a distant world that operates on a completely different biochemical operating system. Our entire toolkit is designed to detect the signatures of carbon-based life, the specific set of 20 amino acids we use, the double helix of DNA, the essential role of phosphorus. But what if another biology used silicon instead of carbon as its structural backbone? Silicon sits right below carbon on the periodic table, and it can form many of the same complex chains. Or what if an organism used arsenic in place of phosphorus? Arsenic is chemically similar, though for our biology, it is a deadly poison. A microbe that incorporated arsenic into its very structure would be invisible to our standard tests, which are designed to find the chemistry we expect, not the chemistry that might be. This is the haunting possibility of the shadow biosphere. It suggests that life could be widespread, even common, yet remain completely undetected because we are only listening for one station on the cosmic radio dial. We might have already scooped up a sample of a shadow organism in an extreme environment on Earth, only to have dismissed it as inert material because it did not react to our biological assays. This conceptual discovery is perhaps the most humbling of all. It forces us to admit that we do not yet know what life is, only what life is here. The universe may be filled with life we cannot yet see, not because it is hiding, but because we have not yet learned how to look. A signal arrived from the closest star to our own. In 2020, the Parkes Radio Telescope in Australia detected a narrowband radio whisper, a tone so pure and specific it stood out from the cosmic background noise like a single, clear voice in a roaring stadium. It was named BLC-1, and it appeared to originate from the Proxima Centauri system, a place we know hosts a rocky world within its star's habitable zone. For a moment, the possibility was electrifying. Had we just received a call from our next-door neighbors? The signal possessed the hallmarks of a technological broadcast, the kind of structured transmission our own civilization leaks into space. The scientific response was a masterclass in caution and rigor. Teams across the globe spent months in a painstaking forensic investigation, testing the signal against every conceivable source of error. They checked for satellites, for secret military experiments, for electronic interference from the ground. They searched for any possible reflection of our own noise bouncing off a piece of space debris. In the end, the most likely explanation was a sobering one. BLC-1 was almost certainly human-made interference, a stray signal from some piece of our own technology that had cleverly mimicked an extraterrestrial broadcast. Yet to dismiss this as a mere false alarm is to miss the entire point. The significance of BLC-1 was not in the signal itself, but in the process it triggered. It was the first candidate that passed every initial filter, forcing our most advanced verification protocols into action. It proved that our listening posts are now sensitive enough to pick up a faint, intriguing whisper from just over 4 light-years away, and that our methods for vetting such whispers are more robust than ever before. We are no longer just passively hoping for a message. We have built a system that can actually put one on trial. This event was a fire drill for first contact, a demonstration that we are actively and intelligently listening to our cosmic backyard, refining our ability to separate the dream of a signal from the reality of one. That fundamental code for life, built from amino acids, was not born on our planet alone. Far out in the dark, a small robotic laboratory was chasing a comet. The European Space Agency's Rosetta mission spent years flying alongside Comet 67P, a lumpy, icy traveler. As the comet swung closer to the Sun, its surface heated up, releasing jets of gas and dust into space, forming a vast cloud around it called a coma. The spacecraft's instruments sampled this material directly, and the data sent back to Earth was unequivocal. They had found glycine, the simplest and one of the most important amino acids, the very kind that strings together to form the proteins that build and operate every living cell on our world. This was not an inference or a hopeful guess. It was a direct, confirmed detection of a life-critical molecule in the wilds of interplanetary space. The significance of this discovery cannot be overstated. It proves that the universe is not just a place where life's ingredients can form, but that it is actively manufacturing them and distributing them across solar systems. Comets like 67P are cosmic ice chests, preserving these fragile organic compounds from the earliest days of a solar system's formation. When they hurtle toward a young planet, they do not just deliver water, they deliver a pre-made starter kit. The glycine that fell onto a cooling Earth billions of years ago could have been the very same molecules that Rosetta found drifting around that distant comet. These icy bodies are more than just spectacular celestial objects. They are the delivery trucks that carried the raw materials for biology to our doorstep. This single discovery provides a powerful, tangible link between the sterile chemistry of space and the vibrant biology of our planet, suggesting that the seeds of life are a universal constant, sown across countless worlds from the very beginning. The same gravitational forces that sculpt the orbits of moons and planets can also forge furnaces within them. This is the power of tidal heating, a relentless internal fire stoked not by radioactivity, but by a constant gravitational tug of war. Look at Jupiter's moon Io, a world relentlessly squeezed and stretched by the immense gravity of its planet and the competing pull of its sister moons Europa and Ganymede. This perpetual internal flexing generates colossal friction, turning Io into the most volcanically active body we have ever seen. Its surface is a constantly changing map of fiery vents and lakes of molten rock, a testament to the raw energy that tidal forces can unleash. This phenomenon completely redefines the concept of a world's energy budget. A planet or moon does not need to be close to its star to be warm. It simply needs to be in a gravitational dance that keeps its interior churning. Now take this powerful concept beyond our solar system and apply it to the countless rocky exoplanets we have found orbiting red dwarf stars. Because these stars are so cool, their habitable zones are incredibly close in. Any planet orbiting there becomes tidally locked, with one permanent day side and one eternal night side. We once thought this would render the night side a frozen wasteland, utterly inhospitable. But if that world is also experiencing significant tidal heating, just like Io, the story changes completely. The internal warmth generated by the star's gravity could power a global subsurface ocean or drive volcanic activity that replenishes a planet's atmosphere. It could provide a stable, long-lasting energy source for chemistry and potentially for life, entirely independent of the faint light from its sun. The frozen, dark side of a tidally locked world might not be a dead end, but a shell hiding a warm, liquid heart, a place where life could thrive in the darkness, powered by the silent, rhythmic pull of its star. Each new world we find deepens an ancient mystery. Decades ago, the physicist Enrico Fermi posed a simple, devastating question. If the universe is so vast and so old, and life is so probable, then where is everybody? This is the Fermi paradox, and with every one of these 30 discoveries, it becomes more baffling, not less. We now know the galaxy is filled with billions of Earth-like planets, that water and the building blocks of life are cosmic constants, and that life itself is incredibly resilient. The universe appears to have all the necessary ingredients in overwhelming abundance for life to flourish. Yet when we listen, we hear only silence. This silence is now the loudest thing in astronomy. One unsettling solution is the Great Filter hypothesis. This idea suggests that at some point between the emergence of life and the development of a galaxy-spanning civilization, there is a wall, a challenge so difficult that almost every species fails to pass it. This filter could lie in our past. Perhaps the jump from simple chemistry to the first self-replicating cell is astronomically rare, and we are the only ones who made it. Or more chillingly, the filter could lie in our future. It could be that every advanced civilization eventually discovers a technology, perhaps nuclear war or a runaway artificial intelligence, that inevitably leads to its self-destruction. In this scenario, the silence we hear is the graveyard of countless species who came before us. But there are other, less grim possibilities. Perhaps intelligent life is not silent, but we are listening for the wrong things. A civilization just a few thousand years more advanced than ours might use a technology for communication that is as incomprehensible to us as a radio signal would be to a bacterium. Their messages might be all around us, woven into the fabric of space itself, and we lack the senses to perceive them. Or maybe they are simply quiet, having learned that broadcasting your location is a dangerous game in a dark forest. They could be observing us, hidden, choosing not to interfere. The very act of searching for life as we know it might be our greatest limitation. We are carbon-based beings using radio telescopes to search for other carbon-based beings using radio telescopes. What if the majority of intelligent life has transitioned to a post-biological state, existing as pure information or conscious energy, entities that leave no chemical signature we can detect and have no need for the worlds we consider habitable? The Fermi paradox is no longer a question about emptiness, it is a question about perception. The universe is not a barren desert, it is a forest teeming with life, but we have only just learned how to see the trees. The silence of the cosmos might not be empty, but filled with processes too subtle for our current tools to grasp. This brings us to a frontier that merges the impossibly small with the grand question of life itself, the field of quantum biology. Here on Earth, we are discovering that life is not just a chemical process, it is a quantum one. The remarkable efficiency of photosynthesis, where plants convert sunlight into energy, relies on a quantum effect called coherence. In essence, particles of light energy explore every possible path through the plant's cellular machinery simultaneously, finding the most efficient route in a fraction of a second. Even the navigational sense of migratory birds seems to be guided by a quantum compass, a chemical reaction in their eyes that is sensitive to the Earth's magnetic field, allowing them to perceive the planet's invisible lines of force as a visual map. These are not quirks, they are fundamental features of how biology harnesses the bizarre rules of the quantum world. Now, stretch this concept across the galaxy. If life on a single planet has learned to exploit quantum mechanics, what could life from a different cosmic environment achieve? Imagine a world with a much stronger magnetic field, or one bathed in a constant, low hum of gravitational waves from a nearby neutron star merger. Life evolving in such a place would be steeped in quantum phenomena from its very inception. It might not just use quantum effects for efficiency, it could be built upon them. Its genetic code might not be stored in a chemical double helix, but in the entangled states of subatomic particles, making it incredibly robust and long-lasting. Its senses might not perceive light and sound as we do, but directly sense magnetic field lines or quantum spin states, experiencing the universe in a dimension we are completely blind to. This is the profound challenge of our 29th discovery. The life we are searching for might not only be chemically alien, its very operating system could be rooted in quantum principles we are only beginning to fathom. Our detectors, tuned for the chemistry of life as we know it, might sweep right past a life form that exists as a stable quantum coherence in the atmosphere of a gas giant, or as a pattern of entangled photons in the depths of space. We are learning that the universe is not just stranger than we imagine, it is stranger than we can imagine, and the greatest signature of life might be written in the silent, spooky language of the quantum realm. The answers we have gathered are about to be tested by the most ambitious robotic explorers ever built. A fleet of missions is being prepared, each one a specialized detective sent to the most promising corners of our solar system. The flagship is Europa Clipper, a spacecraft designed for one primary purpose: to determine if Jupiter's icy moon harbors conditions suitable for life. It will not land, but it will perform an unprecedented reconnaissance, flying past Europa dozens of times at low altitude. Its sophisticated radar will pierce the icy shell, mapping the thickness and structure of the crust to find the ocean hidden below. Its thermal instruments will search for warm spots where the ocean might be leaking through fractures, and its dust analyzer will attempt to capture and identify tiny particles from potential plumes, directly tasting the chemistry of that alien sea. This is not just a flyby, it is a full planetary physical, an examination that will tell us if Europa has the right chemistry, the right energy, and the right environment to be a living world. Meanwhile, on the other side of the solar system, the Dragonfly mission will transform science fiction into reality. This is not a rover, but a nuclear-powered drone, an octocopter designed to fly through the thick, hazy atmosphere of Titan. It will leap from one location to another, exploring diverse landscapes across the alien moon, from its organic sand dunes to the floor of an ancient impact crater where water and complex organics may have once mixed. Dragonfly will land on Titan and literally taste the surface, using its onboard mass spectrometer to analyze the complex chemistry of the material that has been raining down for eons. It will be searching for the very molecular patterns, the prebiotic chemistry, that could lead to a new kind of life, one built for liquid methane instead of water. And back at Mars, the pieces are falling into place for the most complex robotic operation ever attempted, the Mars Sample Return Campaign. The Perseverance rover has already sealed dozens of pristine rock and soil samples, the most promising geological evidence from an ancient river delta. The next steps involve a relay race across millions of miles. A lander will touch down, a fetch rover will retrieve the tubes, a small rocket will launch them into Mars orbit, and another spacecraft will capture the container and bring it home to Earth. In our most secure laboratories, free from contamination, we will subject these rocks to scrutiny far beyond any rover's capability, searching for the faintest microfossils or the subtlest chemical imbalances that can only be explained by ancient biology. These missions are not just about collecting data, they are about collecting answers. Within the next decade, we will move from seeing these worlds as distant points of interest to understanding them as real places with real potential for life. The great silence is about to be broken not by a signal from the stars, but by the whir of a drone's rotors in an alien sky, the gentle touchdown of a sample capsule in a Utah desert, and the data streaming back from an ice-clad world 500 million miles away. These 30 cosmic whispers have painted a new picture of our universe, one brimming with potential. We have not yet found a fossil or received a clear message, but the evidence for life's possibility is now a chorus, not a single, faint voice. From the acidic clouds of Venus to the buried seas of Europa, from the methane rivers of Titan to the tantalizing atmospheric hints of distant water worlds, the cosmos is revealing itself to be a place remarkably suited for biology. The fundamental ingredients, water, organics, and energy, are universal constants scattered across the galaxy like seeds in fertile soil. We are living through the moment when humanity's oldest question transitions from philosophy to active investigation. This is the golden age of discovery, where every new telescope image and every robotic explorer sends back data that could rewrite our place in the cosmos. So the next time you look up at the stars, remember that the quiet darkness is an illusion. It is a canvas alive with hidden oceans, chemical factories, and the faint, hopeful signatures of worlds that may not be so lonely after all. Which of these discoveries filled you with the most wonder? Let us know in the comments and join us as we continue the journey to the very frontiers of what is